All right. Good morning, everyone, and welcome to the College of Arts and Science. I am delighted to have you here, and I would like to first extend my sincere appreciation and thanks to our Dean, Wendy Suzuki, for kindly permitting us to host this lecture at the NYU Silver Center. I also want to thank Mr. Carl Page, the president of the Anthropocene Institute, for sponsoring this lecture and for sponsoring our AI research project here at the NYU Current Institute. The world needs new and expanded sources of clean energy due to the growing global population, the increasing per capita use of energy as countries develop, and the many clear and increasing effects of climate change. The rise in global sea levels is particularly worrisome. Nuclear energy is one of the best options for powering the world now and in the future. And it does not emit greenhouse gases. Importantly, nuclear energies are about 1 million times greater than chemical energies. And one type of nuclear energy is LENR. It stands for Low Energy Nuclear Reactions. It was initially called cold fusion. Today, here at New York University, it is an honor to have with us the world expert in low energy nuclear reactions, Professor David Nagel, who started working in the field in 1989. He has over 60 years of experience in research, mainly at the Naval Research Lab at the George Washington University. Please welcome to the podium, Professor David Nagel.
Okay, thanks for turning on the mic, Adam. Thank you for the invitation and the introduction, Anasse. I very much appreciate it. I am both pleased and privileged to be here with you to talk about a subject which has two remarkable features. One is it's a challenging area of science, physics, nuclear physics in particular, not understood yet, as I will talk about a little more. Oh, and also it has the potential to be practically important, so along with a global community, I'm working towards a situation where you go home, you will have a nuclear power source in your house based on LENR. That's what we're striving for. There's a lot to do before then in terms of the science, in terms of engineering, materials, development, business. It's a very complex area, but that's the vision. So what I'm going to try and do is start with the right slide. Let's go back here. Okay. There we go. Okay. So at our university, people often fall asleep early in a lecture. So I'm going to tell you the bottom line right away. Okay. So the status of LENR, it's real and very promising. What do you mean it's real? It is possible to produce nuclear reactions using very, very, very low energies, chemical energies. Okay. And I will show you some data on that. And then the momentum, it's a field that had a lot of troubles initially. I'll speak to that briefly. It's fairly interesting, the sociology and everything. But right now we have momentum and things are looking quite good, even though the funding is still not what it ought to be. And the potential, as you see here, major applications and impacts are possible, okay? I can make a case for this technology after it's developed, capturing a significant fraction of the world energy market. Let's see, how big is the world energy market? $8 trillion a year. So what if you get 1 part in 1,000? Okay, that's billions. Okay, so we have a very, very high promise here. So that's the high level. Now the presentation is about this new source. It has certain features, and we know these features from experiments. Okay, as Anasse said, the field started in 1989. We've had over a third of a century of experiments in many countries around the world, competent people using good equipment, good procedures, calibrations, and everything. So we know a lot already. And one of the things is that it's possible to get energy gains. Now, some of you may be sitting there saying, let's see, if you put in chemical energies and you get out, of course you get energy gains. Okay, so we'll talk about that more. And because of the high power energy densities, we may have distributed and maybe even mobile sources of nuclear energy. No ginormous power plant with a grid and so forth. We're working towards something that might be on the size of this podium or maybe the size of a desk. The data that's available show that the LENR reactions are safe. They don't emit dangerous radiation, don't need heavy shielding. Oh, wait, no radioactive waste. Okay, amazing. How is that possible? It is remarkable. And of course, being nuclear, it's free of greenhouse gases. So I put this statement here partly to provoke discussion. Pre-cell phones, like half the people in the world had never made a phone call. And of course, it's dramatically different now. So what we expect to happen if this technology makes it to market, a big if, that it will have a big impact, not because of the mobility, but because of the distributed character, because you can have them in homes, okay? And you can turn up your thermostat and the nuclear power source in the basement responds. So that's what we're working towards. Now, this is a simple outline of the presentation. It's about energy. I'm fortunate to be dealing with Professor Bari and his students on AI, so we're going to talk about information. Matter is going to get less discussion here, but if some of you want to talk about it, my background's in materials, give me a day and a half, and we'll talk about it. Okay, but it's mainly to talk about energy and information. And as you know, here's Einstein's famous equation, and a small amount of mass turns into a large amount of energy because of the large value of C. Oh, and it's squared. Now, more realistic outline of the presentation is here. Has 3 parts. We'll start with some high-level considerations of energy. Maybe you didn't think about energy in the last few minutes or hours or days. So I'll try and set the stage there. A lot of the talk on LENR, and then at the end, I'll have several view graphs on the intersection of LENR and AI, which is a rich area of study. So starting at a high level, I remind myself not to fall off here. We get our energy from the movement of masses, air and wind, windmills and dams and so forth, from overhead and underfoot. But it's reactions that are, dominant: fossil fuels burning, also biomass, and nuclear reactions, fission, fusion, and LENR. Okay, so I'm sure you all know this, but I wanted to start at this high level to set things in context. Now, chemical reactions, which involve electron volts. What's an electron volt? It's the energy gained by one electron when it moves through 1 volt. Like if you have a 1.5 volt battery in your flashlight, you get 1.5 electron volts. They're a minuscule amount of energy. And they offer, useful power densities, well engineered, lots and lots of cars. If you haven't thought about the engine in a car recently, stop and think about it. When the motor's revving at 3,000 RPM, that crankshaft's going around 50 times a second. Okay, anyway, think about it. It's very interesting. That's the good news. The bad news is the energy density is not very high. So you have immense amounts of coal and oil and gas, biomass, other things. Oh, and then there's a problem of global warming. And I know a lot about it. I would love to talk more about it, but I'm going to pass over it. So focusing now not on chemical energies, but nuclear energies, the scale is 1 million times larger, okay? Some of the energy that binds protons and neutrons together in a nucleus can be released and used. So this is a cartoon of a nucleus showing the protons and the neutrons. And there are 2 major ways to do that. You can take heavy elements like uranium or plutonium and split them. That's called fission. You probably all know that. It happens when they're impacted by a neutron. I'll show a graphic on that. And on the other end of the periodic table, you can take light nuclei, jam them together, and get energy. Now, some of you may be, how is that possible? Okay, so I'll show you a graph that explains how that is possible in just a moment. So at the bottom is a reminder of what the isotopes of hydrogen look like. The basic hydrogen has only a proton. Heavy hydrogen also has a neutron. Tritium, a radioactive element, has 2 neutrons. Now, these graphics are useful because they remind you what's in these isotopes of hydrogen. But they're a tremendous lie the nucleus is on the scale of femtometers, 10 to the minus 15 meters. The electrons in the atoms on scale of 10 to minus 10 meters. So there's actually a ratio of 100,000 to 1 between the size of the atom and the size of the nucleus. Okay, so you're shooting deuterons into a solid. You know, you want to do an LENR experiment. Just think, you got this large volume with these minuscule. And the nuclei are positively charged. They don't want to get near each other. How is it possible? Okay, so it's a very interesting, dynamic situation that we're dealing with. Okay, so this is the graph that explains how you can get energy out of both ends of the periodic table. On the bottom is a number of nucleons, neutrons, and protons. You see there's uranium-238 up here. And then on the vertical axis is the binding energy per nucleon in MeV. So you see that the most tightly bound elements are in the range of iron 56 here, okay? And you have less tightly bound on both ends here. So if you start with a heavy nucleus, lots of nucleons in it, you get a small change, but in a lot of nucleons, so you can get a lot of energy out of a fission reactor. And that's basically how they work, of course. On the opposite end, if you take these three isotopes of hydrogen, okay, there, 1, 2, 3, jam them together to make heavier elements, you increase the binding energy and you get energy out of that in the form of kinetic energy of products. Okay, so this is a well understood graph from nuclear physics. So I'll give you one graph each, or one graph on fission and a couple of graphs on fusion. So you've seen pictures of these already. Here's a neutron that comes into plutonium or uranium, and it causes two lighter elements to appear. Another neutron goes on, you have a chain reaction. Good news, clean. But the bad news is very large facilities and very, very long radioactive waste. So now some of you are saying, hey, tell me something new. Okay, well, I'll get there. Okay. So this you're not as likely to know about. That's the hot fusion stuff. And this is a cartoon of a facility being built in the south of France. The International Thermonuclear Experimental Reactor. It's costing way over 20 billion, too much for one country. It's a consortium of countries taking way over 20 years, behind budget, behind schedule. And the drawing here shows the scale of the thing. So these are floors. 1 floor, 2 floor, 3rd floor, 5th floor. So this thing is like 50 feet tall, okay? And the plasma here, indicated in pink, is like 15 feet tall and big enough. You can put, it's on the scale of a bus, okay? It's ridiculously large and difficult. You know, there's somebody in back saying, what's the temperature? 100 million degrees. And you have to confine that with magnetic fields for long periods in order to get net energy out of it. So the way it works is you take deuterium and tritium, they're cooked up so hot, they're flying around at speeds high enough that when they approach each other, they can actually make contact and react. Yes, clean nuclear, but large facilities and still significant radioactive waste. So, you know, nuclear fission, the reactors, roughly 400 reactors in the world now, not counting submarines and ships and things, okay? They work, they're good, it's clean energy, it's reliable, and so forth. The hot fusion systems, if they come to pass, you know, 20 years from now, 30 years from now, a long time from now, a lot of work to do yet, then they could be good too. But the thing that is very exciting, I got ahead of myself, for me, is that we can beat all those technologies with our low energy nuclear reactions. Sorry, I forgot about this. While that ITER ground on year after year after year, 15 small hot fusion companies have sprung up. They're listed here. Some of them have a lot of funding, nearly $1 billion of funding on their own. Okay, so there's a lot of money going into hot fusion. Okay, so the cold fusion or LENR field started with this press conference on this date in 1989. Martin Fleischmann, Stanley Pons, a Brit and a guy from the US, had this announcement. And it created immediate excitement. I was swimming laps in the pool at NRL, and the associate director was so excited, he sent somebody down to get me out of the pool and report to him and tell them what's about going. I hadn't even heard of it at that point. Okay, so it was immediate excitement. It reminded me when Roentgen announced X-rays in Germany in 1895. People were afraid that they were going to lose their privacy. You could buy lead-lined underwear the next year. So the way in which this propagated out, this LENR, or then cold fusion, was utterly remarkable. A few weeks later, you had these U.S. magazine covers, all on the same date, May, fusion or illusion, and mistake or miracle, and so forth. It was really interesting, and it was pre-internet, so we were getting faxes of faxes of faxes. You could hardly see. It was a very, very challenging, very memorable, very exciting time. Okay, so now I'm going to get more to the meat of the talk. This is a talk that tries on one level to give you a status and overview, but I want to show you a few graphics that actually have some content, some technical content. So this is a cartoon that shows reactants going to products, and this is the energy. So they start out with high energy, they wind up with low energy, and this is the difference of the energy release. Oh, but wait, there's an activation barrier. Initiation energy is required to get over it. And the scale for nuclear reactions is megaelectron volts. Chemical reactions, electron volts, as I already told you. Both cases, you're putting reactants and initiation energy into the proper conditions to get products and energy release. And this is just an amazing ratio. So the reason there was and still remains so much doubt about this field, about its reality and about its understanding, is that the initiation energies that we're using are just little bitty EVs, but we get out MEVs. It's almost like a cheat. It's like, investing money and getting not a few percent, but factors of return. Venture capitalists like that. It's almost like the venture capital of energy. Now, lots of problems. Am I going to talk about this? Of course not. These graphics will be available, right? So if you want to know why this field has been controversial and remains controversial, I invite you to sit and look at this. But of course, I'm not going to go through it. But it has been interesting. I tell people the only levels on which this field is interesting are wave functions and quantum mechanics, and it goes all the way up to sociology, finance, and so forth. So, people ask me, why am I still working in this? It is really interesting as well as potentially very important. So the field got off to a rough start and was declared dead the same year that it was born. Born in 1989, died in 1989, you see there. And I have a letter from a colleague dated late 1989 that says that, Dave, because you're working on LENR, your career is over. This is a fellow I work with. And, he's entitled to his opinion. Okay, let's see, here I am a few years later, still having fun, coming to nice places like this, talking to smart people. So anyway, that didn't work out, but it has been very, very interesting. So a few hundred of us have been working over the years. Here are a couple of sources of information, Jonah Messenger's article on the top here, and then this website here. So the good news is there's a lot of information on LENR. The bad news is there's a lot of information on LENR. If anyone wants to get into the field, as you students who are working on it know, there's an activation barrier. It's hard to get your arms around. Over 5,000 papers and reports. And I can tell you that having heard most of those over the years, I have a hard time remembering everything, accessing everything, and that's why the project here at NYU is so important. So I have got about a half a dozen graphics now in order that are going to be more detailed. I see most people are still awake, so please stay awake. I can't give a talk on technology without showing a few graphics about plots and data and so forth. So this is intended to legitimatize my being here. Okay, so a standard LENR experiment here has active materials that are placed into it, and then you put in the energy and the reactants, you get out the energy in the products. Conceptually, it's very simple. It can be done on a tabletop. No big facility that takes years or decades and billions to build. Typical experiments can be done for $250,000 or so, some less. But anyway, they're sort of a manageable price. So the key thing is you have to mix and move protons and deuterons in some materials, mixing and moving. And it can be done by a variety of means. You can dry mix the materials initially, bring them together, and then put electrical current through them. You can deposit them simultaneously. You can start out with a material, palladium or nickel or some other material, and load it by various means here. The original technique was Fission and Pond's electrochemistry. Japanese are doing a lot of hot gas experiments. Many plasma experiments have been done. Okay, so it's not a simple recipe, and it's not like chocolate chip cookies. You have a limited number of things. There are lots of options, lots of things. So this is a summary of, as it says on the top, the materials and the methods and the measurements. Mainly palladium and its alloys, although some nickel, okay, deuterium, protons, and mainly heat measurements and nuclear product measurements. The heat measurements use calorimeters, the same kind of an instrument that's used to determine, the calories in the food you buy. You go to the grocery store to look at it, so many calories. Okay, so we're using an old, well-known technology, calorimetry, in order to measure the heats. So you'll see the term excess heat. It is the thermal energy out on top of or in excess of the input electrical energy. Measured with calorimeters, you get power as a function of time, and then you integrate that to get the energy. Now, I see, again, bear with me, you got a few more of these view graphs. So if you take two deuterons, jam them together at high speeds, the so-called hot fusion, you get a 50-50 break on the production of neutrons and the production of protons, okay? With a little fraction, 1 in 10 million, you get a gamma ray. Now, when we do the LENR experiments, you only get a few neutrons, you get some tritons, and almost everything goes into the helium branch. But wait, without a gamma ray. So the plot in the bottom here shows the ratio of helium to energy for 16 different experiments. So the people who published the papers on which this graph is based measure the energy by integrating the power, gotten with a calorimeter, and then they counted helium atoms using a mass spectrometer. They ratioed them, and they found it came out very close to the value for ordinary DD fusion. Okay, so people will ask me, Dave, what's the evidence that LENR actually happened? This is it. It's simultaneous measurements of energy in bodies, if you will, helium atoms, okay, after the experiment, and their quantitative correlation. Okay, so this graph has a lot more that could be said about it, but I'm going to go past it. We can come back to it. If anybody has any questions right now, I'll be happy to respond to them. But I'm not doing justice to this, but I did want to show you that we can measure heat, we can measure helium, and they're correlated, okay? Now, this is the worst graphic that I'll show you in terms of complexity and all. On the left are two experiments. The top one was done in Illinois, and the bottom one in Hokkaido in north of Japan. So horizontally, you have the periodic table, the mass number, okay? The sum of the number of protons and neutrons. And vertically, you have the production rate of elements at that mass number. So these people did experiments, and then they measured all these elements quantitatively, and they plot them up, and they find that there are peaks. They're not well defined. 1, 3, 4, 5 peaks, okay? And they agree with each other. So there are people who are saying that LENR experiments are not reproducible. We have had and still have problems with reproducibility. But there is data like this that shows, I can do something in Illinois, I can do something in Hokkaido, and I basically get the same picture. So setting that aside, on the right is data, this from on the top from Poland, on the bottom from Japan, where you have atomic number. Again, this is mass number, this is atomic number, but it's the periodic table left to right. And inverted plotting plotted vertically are screening energies. What's a screening energy? Well, it's a parameter that's pulled out of the data that is a measure of the rate, the cross-section in physics terms, if you will. So you look at these and you see there are peaks, 1, 2, 3, 4, 5, and they line up. I gave a paper in Poland on this last year, and the only things that we don't know are why peaks occur here, why peaks occur here, and why they match. So if any of you do crossword puzzles or read mystery novels or anything, set those aside and help me figure this out. This is vexing. I don't lie awake at night, but if I wake up at night, I've been thinking about this for decades, and I cannot figure it out. And and it's not because the data is bad; it's my shortcoming. Okay, so I've challenged my friends all over the world to figure out these things. Now, this graphic is one of the last complicated ones. Horizontally is energy density, energy measured in watt hours per kilogram, versus power density, watts per kilogram. And your current and projected energy storage sources and so forth are down here. So here's a lead acid battery in your car. Here's ordinary petrol, gasoline. And here are 3 LENR experiments, okay? And they have a dramatically higher energy density and power density. And that's why we think we can make systems that are small enough to be of this size and go into homes, okay? Now, there are people in the audience who are saying, Dave, 3 lousy data points. Okay, well, there are others. I've gotten only recently from a friend in Europe, which I haven't put on here. They fall out here too. And I'm trying to get funding right now to redo that experiment. Okay, I am really anxious. This was an experiment, Preparata in Italy, reported in 1996. He gets in an LENR experiment power densities that exceed those of a fission reactor. How is it that experiment hasn't been repeated? It doesn't make any sense. So anyway, I'm at a point now where if I have to pay for it myself out of pocket, I'll do the darn thing. Now, this is a totally different graph, and I'm introducing it briefly for a reason. This is Moore's law. You see the date of introduction here, the number of transistors vertically. We're now around 100 billion. Intel says that by the end of this decade, by 2030, there will be 1 trillion transistors on a single chip. Not a million, not a billion, a trillion, 10 to the 12. Okay, why am I showing this graph? We're down here now in terms of LENR. Imagine if the level of effort that has been applied to the semiconductor industry were applied to this. Okay, we would have a very, very different energy situation. Now, I get asked all the time about theories. I'm not a theoretician. There are about 3 dozen theoretical concepts. Very few of them have been adequately developed, reduced to equations, evaluated, and so forth. And this is the beginning of a paper I wrote with a couple of Hungarians, a review paper. But the one-sentence summary is LENR is not understood. Despite all these ideas, despite years, decades even now of work by competent people. There's a professor at MIT who's really good, a friend of mine in Kyiv, so Japan, Takahashi. There's some really, really, really good people working on the theoretical problem. Haven't cracked it yet. Whoever cracks it wins a free trip to Stockholm. It's almost certain to produce a Nobel Prize. Now, what about the science? So we have these international conferences on cold fusion. We've retained that. The 25th one was the one in Poland that I mentioned. The next one is in Japan. We have an International Society for Condensed Matter Nuclear Science. We have a referee journal. If you came into one of our conferences and you listened to the people say what they did, what they found, and respond to questions, you would probably think you're at a scientific conference. This isn't a bunch of nutcakes running loose, as people have sometimes accused us, okay? These are serious people who are spending a lot of effort, a lot of their own time, a lot of their own money to try and figure out this riddle, okay? Now, what about commercialization? There's a company in California, one in Japan, one in Portugal. I visited them last year. There's another in the US. Tadahiko Mizuno, a friend of mine, has a company. He's in Japan, but he has a company in Thailand. So we're working on commercialization. Okay, a company was formed in Colorado in December in anticipation of me getting a patent, okay, to develop a potential commercial LENR generator, okay? And I hope to get the patent, I hope to get the funding, it's $10 million, and to be able to pursue that, try to see how well the patent works, and can it actually be reduced to practice. LENR, the Low Energy Nuclear Reaction Industrial Association, is an organization that a colleague of mine from California and I set up around 10 years ago in anticipation of an industry. This is the LENR ecosystem. I could talk at length about this. You see there are government entities, other organizations, core groups, New Energy Foundation, others, information sources and businesses. So, this doesn't make the newspapers, but there's a substantial set of substantial organizations that are working very, very hard to make this field a reality. So to finish up the LENR part before I get to the AI part, and I think we're doing okay on time. The short summary of the status is I mentioned, it's real. It's been proven many times in the many labs in about 12 countries. The basic physics, as I said, is not understood. And that means that there is a problem with acceptance. Sometimes in science, the understanding is there immediately, like the Mossbar effect. Some of you probably have heard about that. When Mossbar published his initial paper, he had the experimental findings, he had the theoretical explanation, and he later won a Nobel Prize. Okay, I mean, he had it. So we're in a situation like superconductivity. It was discovered in 1911, but was not understood for 40-some years later until Bardeen, Cooper, and Schrieffer published their theory in the 50s. So we're in a situation that's more like superconductivity. We have a gap of decades between the discovery in the 1980s, okay, and the explanation that we're still anxiously waiting for. Okay, the underfunding, I'll speak more to that in a moment. So, as I say, it's a remarkable scientific problem and a promising new clean energy technology. So, what if it were only a good scientific problem? It's still worthwhile. People do science for science sake, generate knowledge. It's exciting, it's worthwhile, it's funded, and so forth. Okay, oh, wait. What if the science were known and it was just a promising new energy technology? Well, that's okay too. But we have both of these things. And it is very, very satisfying. It's very, very exciting. Okay, the momentum. The research has been done, as I said, in several countries. Japan has had a major program for many years. Google funded a program for these years. European Union started the 2 major LENR programs then, sporadic investment in the US, and finally, the United States Department of Energy announced a program at the beginning of last year. So it's seen increasingly as real and promising. Why did I put these 3 in red? It's because they're each $10 million programs. Okay, that gives you a scale of what we're doing. Now, wait a second. I said the hot fusion guys have tens of billions of dollars. We have tens of millions of dollars. But we think that we can produce a more useful technology than they can. And that leads to some pretty interesting discussions. You can imagine. I used to work in a hot fusion community. I know these people. Okay, the potential, and this is a repeat, but it really, really is key. High energy gains. Who's that asked? What's the highest energy gain ever seen in an LENR experiment? The ratio of the thermal energy out to the electrical energy in. 800. Would you be satisfied with 8? You could reduce your energy bill by a large factor. Now, the 800 has not been repeated. It's not been verified. It was done by Mizuno. He's a competent guy. I'll bet the ranch on it that it's right, that he actually got that kind of an energy gain, okay? But other lower energy gains have been reported, a lousy 5 or 10 or something like that. So in any event, it's a situation where we may have much, much cheaper energy because of the high energy gains. High energy densities, I've emphasized that already, and that's a repeat of what I said earlier. So we could have generators, multi-kilowatt thermal and electrical generators in homes, okay? And it's hard to describe how much fun I'm having. You know, I'm 86 years old. I could have retired a long time ago, but nothing I can do with my life would be as fun as trying to understand and commercialize LENR, okay? So I hope you'll tolerate, if not forgive, my enthusiasm. I'm having too much fun. Having fun is a good thing. So here are the two big challenges I just mentioned: understanding commercialization. We have real problems on scaling up the powers from watts and tens of watts to kilowatts. Okay, I could go on and on about that. One of the major problems is the reliability of materials. If you take a material, cause reactions to occur, it heats up. What happens? Diffusion. Relentless. You can't stop it. Okay, and that can degrade the materials. So the materials problems in this field are very, very challenging, very interesting. Okay, now at last I'm getting to AI. Okay, I see some smiles. Okay, so here we have this big literature, and even somebody who's been in the field, who's heard the talks, who's read the papers and so forth, has trouble, is there another paper on titanium hydride? I forget, was it Bavarian in 1960? No, blah, 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 blah. Anyway, so mining of the literature is very, very much needed, and the Anthropocene Institute here funded Professor Bari and his group to develop techniques to take advantage of the LENR literature, okay? And I'll talk about that in the remaining few graphs. I'm nearly done, okay? So I say the NYU program seeking to use available, sophisticated, old and new AI tools to mine the large existing literature for actionable insights. We want to see things that we can't otherwise see because of the limitations of our ability to remember things, okay? It's as simple as that. And the team is designing, developing, and deploying modified new AI tools to support and accelerate current and planned research, development, commercialization, okay? So I am just utterly delighted that this project is going on and it is going on here. So this is the cast of characters. You got these super students here, and you're equally super professor. And we've been at this, this started in the summer of last year, right? Remarkable progress already, okay? And I'll show you some of it in the next few graphs. So let me thank the students who are involved, many of whom are here, for your work on this. You know, this is not just another academic project. You work hard, write papers, you get published, and then you go on. This should matter, and I will tell you more in a few minutes why I think it will matter. Okay, so some of the things that are coming out of it include graphics like this, where you have a plot horizontally of time and the number of papers on LENR each one of those years. You can click on any one of them, and the papers show up here. You can click for the ones that are not behind paywalls and immediately get a copy of it. It's extremely useful. I'm writing a book on LENR. I can't tell you how much I wish I had this when I started the book in 2017. It is really, really useful. Another thing that comes out of it is a connectivity. The dots are individual people, and the size of the dots shows how many LENR papers they have published. Peter Hagelstein is at MIT, Takashi is in Japan, Mukubra used to be in California. My dot isn't very big. I've only published around 4 dozen papers so far. And the gray bars show people who co-authored papers, and the width of the bar shows how many papers they bought. So you had a Japanese guy and a Chinese woman who only published with each other, but they published many papers, Arata and Zhang. Very, very interesting. So this is a fast way to get an idea and an overview. As an aside, Ed Storms, who lives in New Mexico, he's retiring. You know, what's he doing? There's a reason for it. Okay, so he can no longer maintain his lab. So I'm buying his entire lab. 2 weeks from now, I'll be in New Mexico packing up his laboratory to bring it back and use it. He's got some really, really nice equipment. So anyway, this is very useful to those of us in the field. Now this graphic, each dot is a paper. They fall into various categories as interesting as indicated by the color coding. These are numerical measures that enable the people in the NYU project to distribute these. So I can ask a question. Let's see. John Paul Barbarian published a paper on biological transmutations. I forget, 1995. What are the 5 most similar papers? So I can find his paper, and then I can look at the area around that. And by the way, if any of you are thinking, I would like to have this capability in my field, if you're doing a paper in a class or a class project or a master's thesis or a PhD, would you like to have a tool like this? Very useful. So any event, I'm in the book I'm writing, there are about 100 sections, 100 different topics, and I said to have this would be so good. I'm going to get a lot of use out of this while I finish the book. And now, more recently, there's a chatbot been added, and the beta version is here. So you can go and ask questions, show me all the papers that had titanium cathodes. Oh, titanium cathodes with hydrogen. Oh, with deuterium. And very, very many questions that can be asked of this chatbot. I've played with the earlier version of it already, and I can tell you already that it's going to be extremely useful. So those are the characteristics that are coming out of the project. We've had a few presentations last year at the Polish conference. I gave an announcement on the project so that the people in our field would know it's underway. Let's see, Yvonne presented in Tokyo last month a paper with the title indicated here, okay? Long, detailed, meaty, worthwhile paper, available from Professor Bari. Anyway, this is solid research, okay, and useful. So I say those of us in the field are really, really, really happy to have this. This is another paper, a recent paper submitted, as you see here, indicated. So anyway, the project is producing results, and they're very good. So I think this is my last graphic, and it says, who's going to use the capability to develop at NYU? Well, let's see. People like myself working on LENR. We can use it, to rapidly and creatively search and use the existing literature. Writers, people write on this, and some of the articles are awful. I mean, I have written numerous emails to authors of LENR articles in the press that don't do a good job. So if they want to learn more about both the large and the small aspects, they have tools. Newcomers to the field, 5,000 papers, what do I do? Okay, going to find it useful, and then, even students will use it. The nuclear science professor assigns a project on LENR to somebody. This is a good starting point. Okay, so I want to emphatically thank you for the opportunity to talk with you. Okay, appreciate your coming, and I hope you enjoy this. If you watch a soccer match or a football game, you know the answer in a few hours. This will take a few decades to play out. It's slow motion, but if I've sort of given you some feeling that it's worth watching, keep an eye on it. During your lifetime, we should understand it and, I believe, commercialize it. Okay, not during mine. Okay, but you should be able to watch this play out and be able to go to the hardware store and buy one. So that's the end of my my talk on LENR and AI. I want to make another point later on, but for the students, just before I quit. But let's open up the floor to questions and complaints, criticism, arguments. I tell people I've been married 60 years. I'm used to really, animated discussions. So anyway, if you have any concerns, you want to clarify, sir. Thanks, Anasse.
Hi, Professor Nagel. Thank you so much for this presentation, and thank you so much for introducing this topic to us. My name is David Chen. I'm currently a senior here, and I want to ask the question of, I know that there's still like a small amount of nuclear radiation from this LENR technology, and I was wondering, I know that radioactive waste can store a lot of potential energy from like the stable elements and atoms inside it. So I was wondering, is there a way to put that extra waste energy into use or no?
Yeah, so to rephrase your question, you mentioned radiation from LENR. It's very little and easily shielded, so we can just set that aside. But the core question is, you have all this radioactive waste that's accumulated on the sites of fission reactors, still has a lot of energy in it, or else it wouldn't be dangerous, right? So can it be used? And the answer is a definite maybe. There are people who are working hard outside of LENR in order to capture that thermal energy that comes from radioactive decay. And some of you may know about radiothermal generators. What's that? It's a radioactive material that makes heat, and then a thermoelectric material turns heat into electricity. That's what powers these deep space probes like the Voyager probes and so forth. Okay, so that's a practical use of the heat that comes from the decay of radioactive materials, such as fission waste. Now, so I don't keep up on non-LENR efforts to capture that energy, but I have been part of a discussion. Can LENR be used to remediate radioactive waste from fission reactors? In other words, speed up the reactions. And I have two concerns. One is there's no experimental database for that yet. Two colleagues of mine from Kiev and Moscow did experiments with cesium-135, if I remember correctly. I'm not sure of that. But anyway, they show that you could speed up the decay by using LENR, but there are many, many different radioactive isotopes in fission waste. So you have to show that each one of them works, because if one of them doesn't, then you're stuck, okay? So and then there's the other problem. Imagine handling all that radioactive waste, getting it out of the casks, putting it in an LENR reactor, everything would get hot, you know. So I am of the opinion at the moment that it's unlikely that LENR will be used to extract additional energy from radioactive waste, okay? I've been wrong many times, but that's my view right now. So thanks for the question, David.
Hi, Professor Nagel, thank you so much. First of all, your talk was amazing. Your dedication and enthusiasm, it's really amazing. Thank you. And my question is, as a new learner, let's say the basics, in order to learn the basics of hot fusion versus cold fusion, right? I think we should start from this point. Which resources you suggest us to read?
Well, it turns out I just happen to have a paper on hot and cold fusion, which I'll send you.
Okay, perfect. Thank you. Thank you so much.
But now this is going to raise a variety of opinions. I'd go to a chatbot, okay?
We will definitely use the chatbot.
Yeah, not ours, but a general chatbot, you know, ChatGPT or Grok or one of these, and ask whatever questions you want to ask. You know, give me a 2-page summary of how hot fusion works. Give me a 2-page summary of how cold fusion works. Give me a comparison. And, you know, maybe all of you do this already, but I get recommendations. Dave, read this book. Dave, read this. I don't read full books anymore. I don't have time for that. I just go to one of the AI things and say, give me a 2-page summary of the book. Is Professor Davis in the group? I guess not. So I did that with his book. Okay. So any event, that's a somewhat facetious but serious answer. You know, go to a chatbot. You had another question?
No.
Follow? Okay, good. Thanks.
Yeah, hi, my name is Vivek, and I was studying physics a million years ago. And just wondering, where do you see the obstacles at the theoretical physics level? I mean, is it like Schrodinger's equations, multi-body, like on the, I mean, are there theoretical blocks? Are there like computational like obstacles? And how can AI help, you know, the scientific machine learning, all the physics-informed neural networks, which is all the, you know, hot stuff right now? Would that have an impact? So just high-level commentary would be welcome. Thank you so much.
Yeah, the sorry theoretical situation in our field is an irritant to me. I wish things could be developed more. So let's start at the top. Either it's going to be explained by standard physics or not. And I have colleagues who have even written books saying that it isn't going to be standard physics. We've got to go outside of the standard model in order to understand LENR. Well, if that's the case, it's going to be historic in physics and in nuclear physics. Then there are people like those Hungarians with whom I wrote that review who say, oh, no, we can do this with standard second order quantum mechanics, and they grind away on it. So the key problem is we have all these concepts, you know, it depends on how you count, 2 dozen, 3 dozen, lots of concepts. And in order for them to be useful, they have to have equations written down based on the concepts, numerical calculations done on the basis of the, and then the numbers compared with experiments. And people haven't been thorough, okay? Takahashi in Japan has been thorough. Some few people, Hagelstein at MIT, but in general, the theoreticians in this area have not been diligent, you know, cranking through the whole program so they can make head-to-head comparisons of the same graph with experiment and theory. I hope that is a satisfactory response.
Thank you very much. Just wanted to, you pointed out that federal government was putting in $10 million recently. I saw that announcement from ARPA-E,
Yeah.
and that's distributed over 8 or so different projects. Wonder if you can comment on where you see the likelihood of success or confirmation from any of those.
Okay. Thanks for that question. That's very timely. From my perspective, the goal of that program, the ARPA-E program on LENR, is too low. They want to show to the physics community in the US and abroad that LENR is real. And you know, my religion is we've got enough data already to show that it's real, okay? But they have chosen some very, very good contractors, okay? I know most of the people. And it's highly likely that out of that program will come some bulletproof evidence about the reality of LENR, that it actually occurs. But as I say, I'm long past that, having looked at the literature, talked to the people, visited the labs, gone to the conferences. I'm convinced already of the reality of it, potential utility of it, and I'm spending my time, I say, partly trying to commercialize it. So it's a good program. The individual contracts are good. The guy at Berkeley, Schenkel, is going to do a good job. He's very, very competent. So I expect good, defendable, acceptable scientific results to come out of it. But they're not going. There'll be a step towards understanding. There's no theoretical work in it. I don't think the theoretical problem will be resolved by that program, and there sure is going to be no commercialization out of it. Okay? So it's good but not great, in my view. You want to argue?
I would just say that if you could reveal the underpinnings of the then that will help you.
I thank you. I'm glad you spoke up. Yes, because if you know what comes out of a reaction, you know a lot about the reaction. That's why the chemical analyses of the so-called transmutation products is really important. So if the ARPA-E contractors do what I expect them to do, a thorough job in all respects, on the input side, the output side, and so forth, they will produce useful information that will constrain theory, and that is useful. Thank you. I appreciate that. Sir.
Hi. Thank you for coming. I'm Irvin. I'm a master's student studying math here. One question I had. So AI has had exponential growth lately, especially, I'm sure everybody in here is aware of that. And obviously that'll come with more advanced models and more energy requirements, do you feel more of a responsibility to expedite research progress in LENR to account for that?
Yeah, thank you. And in fact, I can go back to the AI part of an earlier question. My expectation is that AI is going to be incredibly useful for mining the literature that's available. Whether or not it will be useful for developing theories or future insights is a much more open question. And I'm utterly delighted that part of the program that we're sharing here involves the question of, can AI create? You know, the essence of science is creativity, right? You have ideas and you follow up on them and so forth. So students who are in the room who are in the creativity program, right? Yeah. So these three fellows are working with Professor Anasse and me on the question of, can AI create? Forward-looking thing. You know, can it produce knowledge that wasn't available in the training set? And that's a work in progress. You know, there are people who say, wow, it never happened. But we'll see. You know, things emerge out of these AI programs. So I say I am utterly, absolutely certain that AI is going to prove useful in using the available information on LENR. I am not sure at all that it will solve the theoretical problem. Is that what you asked? Okay.
We still have a few minutes, so we'll.
Thank you. Hi, Professor Nagel. My name is Julius Balbus. I study data science here at NYU. I thank you for coming here to speak to us. I definitely do look up to your enthusiasm about LENR, and I'm just curious, what were the guiding factors that built up your enthusiasm despite the early controversy? Because I mean, I saw that huge list, and it takes a lot to stay committed to something when people think that you would be out of a career.
Yeah, well, thanks for the question. So there were two reasons for it. At the time of the announcement, I was the head of a 150-person group of nuclear physicists and solid-state physicists. So it was in my sandbox. You know, as an employee of the government, I had an obligation to look at it, okay, because, you know, it was potentially important, and the taxpayer was, you know, paying me to pay attention to things, okay? So that's how it started out. So then I stayed with it, and I had a long time, the order of a decade, where, you know, I had serious concerns about the quality of the data and everything that's going on. And I gradually and eventually reached a place where I could not see all of that information. Again, I've said this, by competent people with good equipment and calibrations and explanations and everything, being wrong, you know, made up or mistakes. Could not see that, okay? Some friends of mine did a Bayesian analysis on it that showed that, you know, for sure it's real, okay? So it was an initial thing. I had to pay attention to it, and then gradually turned into a personal addiction. So if you want to understand me, I'm the scientific equivalent of a crack addict. And thanks for the questions.
In the hot fusion community, do they also identify that there is some missing piece to their puzzle as well? Because I don't see how this only occurs with cold fusion if it's a fusion phenomenon. Does it also occur in the hot fusion as well?
Yeah, that's a very, very good question. Hot fusion is understood physically. You have the particles flying around, they connect with each other. Beam experiments, the accelerators have shown over decades what comes out of it. You know, so it's understood, but the engineering, the ability to confine a plasma that's 100 million degrees for minutes at a time is a daunting engineering problem, okay? So hot fusion, physics understood, engineering problem. Cold fusion, if you will, LENR, physics isn't understood. Oh, and we still have an engineering problem, the material's durability and the like. Okay?
Professor, thank you so much for your fantastic lecture. I respect you so much for throwing yourself in this industry that may require decades or generations to develop. And I really anticipating the bright future of this LENR technology. Well, I have a question. In previous slides, you have shown that scientists have found 5 energy peaks of this cold fusion. Does that mean that there are 5 possible technology paths for this to develop? And have we found that which path is shown to be more promising and economic and effective?
Yeah, so you're asking about the peaks in that one graphic. Yeah, it's likely that the same physics is producing each of those peaks, okay? And I could go on with some details, but I don't think that they provide alternative paths to realizing the commercial promise of LENR. The basic issue is, do we use electrochemistry to mix the protons or the neutrons with the material, or hot gases the way the Japanese are doing, or low temperature plasmas like in a fluorescent light, or high temperature discharge plasmas, arcs, if you will. And I'm betting the ranch that it's on low temperature plasmas like the plasmas in fluorescent lights. So that's the patent I'm seeking, okay? So it has nothing to do with the peaks. It has to do with the alternative approaches to producing the mixing and the motions of the hydrogen isotopes with active materials. Okay, thank you.
Hello, Professor. Thank you very much for coming today.
Thank you.
My name is Peter. I'm a sophomore here at NYU. And in terms of commercial application, how quickly do you think you'd be able to scale a possible application? And also in terms of like financial accessibility, would like a possible application be accessible to parts of the world that may not have adequate energy resources?
Yeah, so the how soon question is a burner, and I've said it's going to take on the order of a decade and maybe more, because if you look at the standard product development, I have a list of 18 steps that are necessary to develop a product, you know, like this microphone or this podium, you know, there's a lot to do. And given the fact that we still don't understand it, and that we have major issues about materials and reliability, controllability, I didn't speak to that, but you know, how do we turn this up, turn it down, turn it off? You know, it's another whole issue. So the commercialization will not be quick. And in fact, I put this in writing already, it won't head off climate change. It's not going to be available in soon enough or large enough, a big enough fraction of the overall energy market to head off the dire effects of climate change. And I am of the expectation that inland migration is going to be one of the hallmarks of our granddaughter's lifetime. They're 8 and 13 now, okay? And that people are, you know, going to have to abandon coastal cities. How many times is the New York subway going to have to flood before people start thinking about moving out of New York? You know, I mean, this is, you know, it's not mysterious. I mean, imagine if you had a flood that would stop you from getting to work on a regular basis, you know? So anyway, LENR, if it comes to market, may come to market in time enough to power inland migration, the establishment of new communities in places that don't have problems with sea level rise. Okay, that's not a very cheery answer, but that's my view right now. Okay. So if there are no other questions, I could make some final comments. Yeah. So I'd say this to the students. You have 2 lives, personal life, professional life. And as you go forward, they have to be in balance. You know, if you're totally taken up with your professional life, you know, your personal life isn't going to be good, and vice versa. So there's a balance there. Now, on the personal side, there's a balance between taking care of yourself and taking care of others. And also on the personal side, you have to do certain things. You have to manage stress, eat reasonably, and exercise regularly. You know, I mean, it's just mandatory, okay? On the professional side, you have to balance learning and doing. If you only learn and don't produce, you're gone. If you only produce, you're going to be taken over by the changing world that we live in, okay? So let's think forward 50 years, no, 15 years, no, 5 years, well, 5 months. I run into you, any one of you, and you look at me and say, I've seen you before. Oh yeah, that was at NYU. Let's see, what did you talk about? Balance, that's the word I want. Balance in life. You will forget about the details of LENR, but I would like you to go forward with a built-in viewpoint for the rest of your lives about balancing these various competing factors. And the reason I recommend this to you is because I had to learn it the long way. It took me a long time to arrive at a situation where that was my view. Now, some of you may say, I'm out of balance. I seem like a professional nut, but you know, I've been married 60 years, and when I left home yesterday, I was still married. You know, dear. Anyway, the point is, as important as energy is, as LENR may be, I would like you to come out of this presentation with a deep-seated view of balance, okay? And as far as exercise goes, I started exercising in my early 40s when I developed a medical problem. I've exercised over 10,000 times, you know. It's part of life. Just like Nike says, just do it. So I wish you the best in your careers and to make good decisions and have a happy life. Thank you very much.
I hope you enjoyed the presentation. Thank you very much, Professor Nagel. I'm looking forward to continuing joining efforts with you and with a lot of our students here that worked with us since the summer. We have almost all the team here, and we're looking for more students to work with us on using AI to expand the field like LENR, as well as we're starting a new project with a lot of the students here on Can AI Create? And we're looking forward to work with all of you. Thank you again for being here with us today, and I wish you a wonderful day. Thank you.
Appreciate it. Thank you.